Uh, Welcome to this special lecture on optimization. This is a part of the course which I am giving on the foundations of optimization, and these special lectures would come at the very last, and it would be an addendum to what is not being told there, but if you have learned what has been there, you can understand what will go on here. So, I would like to welcome Professor Vishnu Narayan of IIT Bombay Industrial Engineering and Operations Research, who is an expert in convex and discrete optimization. So, to give this lecture on how to model optimization problem with integer variables. Thank you very much.
Okay, welcome everyone. So, as Professor Joydeep Datta said, today I will be talking about formulating certain problems as integer programming problems. So, first of all, let us see So, first of all, let us see that integer programming is a different problem from linear programming. There are certain issues that are not resolved that are present in integer programming problems. So, let us look at a really simple two variable example. So, what I want to do is to maximize 20 x1 plus 21 x2 subject to one constraint which says that 10 x1 plus 11 x2 is less than or equal to 33. I also have x1 and x2 are non-negative integers. So, here is a really simple problem, two variables, just one constraint with both variables supposed to be non-negative integers. So, if we look at the feasible region of this integer programming problem, so we have x1, x2 and the feasible region or the constraint is going to look something like this, and the feasible points are all the integer points with inside this triangle, which I am going to mark in red. So, these are the feasible integer points, and the one in the corner. Okay. Now, let us try solving. So, let us first of all let us ignore the integrality constraints and try solving this as a linear programming problem. Now, it is a very simple linear programming problem by whatever your favorite method is. You can see that the continuous optimal solution or the linear optimal solution is this particular corner point. So, we have a corner point here, this is the continuous optimal solution. So, the continuous optimal solution which is the point 3.3, 0 with objective value 3.3 multiplied by 20 is going to be 66. Now, if we look at the nearest integer point to this continuous optimal solution, then it is this point 3, 0. So, this one is the nearest integer solution to the continuous optimum, which is 30 and its objective value, as you can compute, is 60. However, if you look at all integer points, you can see that the integer optimum does not lie anywhere near the continuous optimum solution. The integer optimum is this point 0, 3. So, this is the integer optimum. Oops, 0, 3 with objective value being equal to 21 multiplied by 3, which is 63. So, now one can also generalize this type of an example to see that the integer optimal solution may be really far away from the continuous optimal solution. So, that is why integer programming requires separate treatment than just linear programming problems in general. Now, first of but today I am not going to talk mainly about the structure of these problems. I am going to talk about posing different problems as integer programming problems. So, here we saw an example of an optimization problem where the variables are inherently integer. However, there are a lot of examples from real life situations where you are not given any integer variables, but in order to model problems effectively you indeed have to use integer variables. So, let us look at some examples of those kind today. So, first of all, so suppose we have the following situation. Suppose that y, z1 and z2 are variables in an optimization problem okay. So, suppose y, z1 and z2 are variables in a particular optimization problem, and they are related by the following: y is greater than or equal to the maximum value of z1 or z2. If this is the case, then we can write, or if you want to represent this constraint, an easy way of representing this constraint is the following. I can simply write y is greater than or equal to z1 and y is greater than or equal to z2. So, these are two different constraints, and this makes sure that y is always greater than or equal to maximum of z1 and z2. This is not an issue at all. However, on the other hand, suppose so if we call this as, let us say 1, the constraint 1 can be modeled easily, fairly easily. But suppose if we have a different constraint, suppose what we want is y is greater than or equal to the minimum value of z1 and z2. Now, here there is an issue. So, here first let me try to demonstrate that this cannot be written as easily as writing these two constraints. Okay. So, the reason, suppose this is called 2, and let us look at the set S. Let S be the set of all y, z1, z2 such that y is greater than or equal to the minimum of z1 and z2, right. So, what I am looking at is I am looking at all possible values of y, z1 and z2 which satisfy this constraint 2. Now, I am going to show you that this set S is not convex. So, if S is not convex, clearly it cannot be represented using linear inequalities and linear constraints. So, that is why I can show you that we require something additional in order to write this constraint 2 effectively. So, let us consider these the following points. So, I can look at the following points 1, 2, 1 and 1, 1, 2. So, here the first coordinate represents y, z1 and z2. So, here in the first point the smallest of z1 and z2 is 1 and y is greater than or equal to 1. So, that is fine, and similarly I have just permuted or exchanged z1 and z2. So, that is also fine. Now, let us take a convex combination of this. So, let us now these 2 points are clearly in S. Now, let us take the midpoint of the line segment joining these 2 points. So, half 1 to 1 plus a half multiplied by 1 1 2. Now, this is going to be the point 1 3 halves and 3 halves. So, clearly here in this case y is smaller than both of z1 and z2. So, clearly this is not in S. So, S is non convex, and therefore, we cannot just model this using polyhedral constraints. So, we will see that we will require we will essentially see that we will require binary variables in order to model this constraint effectively. The exact model I am not saying right now, because we will see this in a much larger context. Okay. So, I hope I have convinced you that there are certain situations where to represent some non convex feasible regions we do require binary variables. Okay, let's see how we can do this. So, what we want is y greater than or equal to the minimum value of z1 and z2, which I can write as y greater than or equal to z1 or y greater than or equal to z2. So, essentially what I want is the disjunction of these two logical of these two inequalities. So, I want either this inequality to be satisfied or this inequality to be satisfied. So, that is the whole idea. Okay. And this I can again rewrite as if y1 is less than z1, then y2 is greater than or equal to z2. So, essentially you can either write it as a disjunction or an if then else kind of a statement.
The disjunction in this thing, the union type thing.
Yeah, disjunction means the or the union essentially. Okay. So, let us look at an application where this type of statements, this logical or type of statements appear naturally, and the application that we are going to talk. Oh, sorry, that is y. So, either y, if y is less than z1, then y must be greater than or equal to z2, or I can say if y is less than z2, then it is all the same. Yeah. So, let us look at a concrete application of or where this kind of constraint set applies. So, this application comes from scheduling. single machine scheduling. So, the problem is as follows. Now, what you have some number of jobs, let us say that there are n jobs to be processed on a single machine, right, and we have the following data. The data is the processing time. So, we know that Pi is the processing time of job I, so we know what is the time taken to execute this job. Now, what our objective is the following. Now, so we have these jobs. What we scheduling on a single machine means to decide the sequence in which the jobs are going to be processed. I mean, everything else is sort of fixed. So, what we want is the question that we want to answer is the following: what is the order in which the jobs need to be processed to minimize sum of completion times. So, this is a question. Now, this idea of sum of completion times is a fairly standard objective function in scheduling. So, I am not going to go into more details on why this is important, but suppose I have this objective here. So, now clearly suppose if I start processing, so let us say that let Ti be the start time of job I. So, we start processing job I at time Ti, then the completion time is nothing but of job I is nothing but Ti plus Pi, and what we want to minimize is the sum of all Ti's, Ti plus Pi's, which essentially means that we want to minimize the sum of all Ti's because Pi's are constants. Okay. So, how would you do that? Now, here is where we have some sort of a necessity to invent binary variables in order to formulate this problem as a mathematical optimization model. So, we are going to use the following binary variables. So, let us use the following binary variables. I am going to create a binary variable xij, which is going to mean the following. So, xij is going to be 1 if job I is processed before job j and 0 otherwise, right. And just for emphasis I am going to say that it is not necessary that job I is processed immediately before job j, it is processed can be processed any time before job j. Now, I hope you are convinced that if I know these xij values, I know the order in which the jobs are processed. So, because I know if you give me job I and j, I know which one is processed first. So, this gives me the complete order in which the jobs are being processed. So, our optimization problem then becomes the following. Then becomes the following. So, what we want is to minimize summation I going from 1 to n T I, the remaining is a constant subject to. Okay. Now, what are the constraints? The constraints say that the constraints say that must give some idea of the sequence in which jobs are being processed. Now, if you think of it, I have job I have job j, only two things can happen, either job I is done before job j or job j is done before job I, that is the only. So, for every pair I can say that, and those are my constraints. So, my constraints are either I before j or j before I, and this is true for all pairs I not equal to j. And I can rewrite this essentially, this is essentially the same as saying that. So, when is job I being, when is job I processed before job j? That means that job j can start only when job I is complete. So, this means that either Pi plus Ti is less than or equal to Tj, or Pj plus Tj is less than or equal to Ti. So, this is this is the constraint that I need to model. Now, this is essentially same as S less than or equal to, yes, j has been completed before I, again for all pairs of jobs I and j. Okay. So, now once we know this, we can essentially write what is the complete mixed integer programming formulation. So, this is the complete optimization problem, looks like the following. So, we have our objective that we had it in the last slide itself. I want to minimize summation of Ti's subject to, yes. So, the integer variables are going to tell you which jobs are done before. So, it is going to give you the sequence essentially. So, Ti plus Pi less than or equal to Tj, Tj plus Pj less than or equal to Ti. So, I know that this is incomplete, but we will come back and complete it later. I just want to fill in the standard constraints. So, I also need to say that Ti's are greater than or equal to 0 for all I going from 1 to n. Then I also have the relation between xij's plus xji is equal to 1. I need to say that if I is processed before j, then j is processed after I. So, this is true for all I not equal to j, and finally xij's are binary variables for all I not equal to j. So, this is essentially the trivial parts are filled in, but now what we need, what we want is, if we look at these two constraints, we want to say that either this is true or this is true. So, this is a very standard trick in mixed integer programming, and here is what I am going to do that. So, what I am going to do is I am going to add something, I am going to say this is, I am going to add some 1 minus xij, and here I am going to add plus m multiplied by xij, and again this holds for all I not equal to j. Yes, that is the whole thing. Okay. Now, here m is a very large number. Okay. Now, let us examine what happens. So, suppose Ti plus Pi is greater than Tj. So, if Ti plus Pi is greater than Tj, the only way this constraint becomes feasible is when xij equal to 0. If xij equal to 1, this term vanishes. So, Ti plus Pi cannot be greater than Tj. So, if Ti plus Pi is greater than Tj, then xij is 1. Okay. Sorry, xij is 0. If xij is 0, then Tj plus Pj must be less than or equal to Ti. So, that must hold. And similarly,
is 0 or 1? No. Xij is 0.
xij is 0, yes. So,
which means the jth one came before ith one.
Yes, and that is given by this constraint. If xij is 0, then Tj plus Pj must be less than or equal to Ti. So, if xij is 1, then Ti plus Pi is less than or equal to Tj. So, that is the idea of this formulation. So, this using these binary variables, we can clearly get this distinction, and let me say that here m is a very large number, and let me also mention this explicitly. So, if xij is 1, then this implies that Ti plus Pi is less than or equal to Tj, and if xij is 1, the second constraint says Tj plus Pj less than or equal to Ti plus some very large number, which does not really say anything, because that is a very weak bound. And similarly, xij is 0 will imply Tj plus Pj less than or equal to Ti. So, this is exactly what we want. Okay. Now, before going to the next sort type of model that I want to talk about, let me just say that although this formulation is correct, this is a correct formulation, this models the situation correctly, but it is not at all efficient. In fact,
I want to ask you what
yeah.
happened if I just do not have the m there and just add plus 1 minus xij?
Oh, so then how do you make sure that, so it will depend on what the values of Pi's are. If the processing times are very large, yeah. So, in fact, you can take m to be the sum of all processing times. That is the least that will make sure that this is going to work. Let me tell you that this is not an efficient formulation at all. In fact, this problem is an easy problem. So, if I want to solve this problem, I would just order the jobs by the shortest processing times and then go on doing that, and it can be proved that there is a very nice submodular a polymatroid which represents this situation using submodular functions, but in order to prove that it takes some time. So, I am not going to the details, but there are other efficient models. So, just because a model is correct does not mean that it is a good model. So, that is the take home message from this part here. Okay. Now, let us go to a very interesting type of models. What we want is to model piecewise linear functions. What do I mean by that? So, suppose I have these are functions of one variable. So, x is one dimensional object f of x, and suppose we have some kind of piecewise linear function. Non-convex, non-concave, arbitrary piecewise linear function. So, it happens that in several practical applications you would have these piecewise linear functions. So, for example, involving fixed costs or things like that, where you need to model these, and it is essentially important, and we can and it is easy to see that without binary variables. I mean, obviously this cannot be written as a if you want to somehow model the piecewise linear function, you cannot do it easily unless it is convex or concave. Otherwise, if it is arbitrary, it is not very easy to do it, but with binary variables we essentially can do it, and that is what I want to show you now here. So, suppose that what we have is we are given this piecewise linear functions in the form of these breakpoints. So, suppose our input is the following. Is our data is of the following. We know points a I comma f of a I. So, what I mean is that this point here, suppose we have this point. So, this is A2 and here is f of A2. So, we are given the breakpoints, and we are assuming that between a I and a I plus 1 the function can be linearly extended. So, this is the whole input that we get. Now, let us look at the following. So, this is A3 similarly. So, let us simplify the problem. Now, let us assume that we are between A2 and A3 or between a I and a I plus 1. So, if x belongs to the interval a I comma a I plus 1, then I can write, and suppose I can write x as lambda a I plus 1 minus lambda a I plus 1, where lambda lies between 0 and 1. Suppose I can do that, then I know that f of x is going to be given by the linear approximation. This is fairly straightforward. So, if x is somewhere between A2 and A3, then I can look at f of A2, f of A3 and do a linear interpolation and then see that that is a value of f of ai plus 1. Now, what we so that is fine, yes. So, we know that. So, now what we are going to do is we are going to exploit this fact and then write a particular mixed integer programming model for doing this. So, what we are going to do is we are going to keep track of which piece is does our point lie in. So, if we know which piece our point lies in, then we know that from the endpoints we can in fact calculate the function value. So, we are going to define the following binary variables for that. So, our binary variables, let me call them as Zi. So, Zi is going to be 1 if my x belongs to this interval, open on the right because I want to avoid confusions, and up to n minus 1 and 0 otherwise. So, using these Zi's we can keep track of which piece we are in, and then let us try to so suppose we know which piece we are in, then we can really write down what the constraints are. So, for example, now what we could do is we could write the following. So, let us first write something and then see what is wrong with it, and then we can try to make it you can try to correct it. So, let us say that so suppose we write x as summation I going from 1 to n lambda I ai summation are greater than or equal to 0. So, essentially what I am doing is I am writing some my x as some convex combination of all these ai's. What I want is the following: I want to write f of x as summation I going from 1 to n lambda I f of ai. However, I can't do that directly because I do not know which piece my x lies in. If only I know that with lies in which piece, then I can make sure that this is done. So, in order to do so, in addition to this, we need some extra conditions. So, let me call this as, because this is part of the formulation. So, let me call this as star, and then we will see what additional things we need. So, what additional things we need? Now, we also need to specify that x lies exactly in one piece. So, we need to make sure that Zi is 1 only for one particular I and not for any other i's, right. So, in addition we need the following. One, exactly one Z I is 1, others are 0, and 2, we also need to make sure that if Z I is 1, then x lies. So, what is Z I? Z I is 1 if x lies between A I and A I plus 1. So, if that is the case, we need to make sure that I need to write x as a convex combination of A I and A I plus 1, right. So, I need to make sure that all the other corresponding lambdas are equal to 0. So, here is what I need to make sure: if Z I is 1, then lambda I and lambda I plus 1 can be positive, but all other lambda j's are 0. This is what I want to enforce, and let us see how to do that. So, to enforce 1 is fairly routine. So, to enforce 1, I can easily write summation I going from 1 to n minus 1, Z I is equal to 1, and of course this will make sure that exactly one of the Z I's is equal to 1. But for the other part, so I am adding all this, these are all integer variables, they must sum to 1. So, exactly one of them is 1, others have to be 0. Yeah. And for the other one, there is a really neat trick. So, let me tell you what because I say that whether x is in the interval a I comma a I plus 1. So, only up to n minus 1, it is just notation, nothing. So, for the other part, here is how.
Why I equal to 1 to n minus 1, that is, so you are summing the Z I's.
Yes.
I equal to n minus 1 on all the points.
I did not understand your question.
The sum of the Z I's.
Yes.
Or I is varying from 1 to n.
Yeah, no, Z I's are only defined up to n minus 1. Yeah. Yeah. So, here is a way to do it. So, let me just state what it is and then we can discuss for a minute. So, lambda 1 is less than or equal to Z1, lambda I is less than or equal to Z I minus 1 plus Z I, where I goes from 2 up to n minus 1, and finally lambda n is less than or equal to Z n minus 1. Now, let us see what is happening here. Now, suppose let us say Z1 is 1, others are 0, what happens? So, if Z1 is 1, lambda 1 can be positive, lambda 2 is less than or equal to Z1 plus Z2. So, lambda 2 can also be positive, but all other Zi's are 0. So, all other lambdas must be equal to 0. So, similarly, so that is why we can make sure that if Zi is 1, then exactly lambda I and lambda I plus 1 can be positive, but all the remaining lambdas must be equal to 0. So, if we use these, so if I call this as say and these guys as, so all these together the piecewise linear function. So, I am stop. So, at least I hope I have been able to convince you that there are some situations where although the discrete variables are not part of the model, I mean intrinsically part of the model, we usually have to use them in order to write these problems as optimization problems. So, there are a lot of these like that. Okay, thank you.